My name is Gerald Mücke, and I'm like to give you an introduction into mutation testing. Shortly about me, I'm self-employed. I run my own little company. At the moment, I'm more in the performance analysis work. But from my experience and my past, I do a lot of test automation. And since around 2 years, I'm practicing mutation testing, which I'd like to introduce to you. Well, in software development, we all, let's say, want to produce good software. So the software has to have an effect, and we try to make the software as efficient as possible. So apparently, we'd like to be in the upper right corner here. Sometimes you have to make concessions, and let's say because of budget constraints, time constraints, resource constraints, so I have to, let's say, reduce the effort, like doing less QA, doing less documentation, doing less work for maintenance or for operation stuff. So, I mean, when you're not in that area here, you probably want to be here. This is usually where startups are. So they have more constraints, have to ship the product to get faster feedback, and probably do less quality assurance. More older companies or bigger companies, they are sometimes in the lower left area here, where they try to adopt to introduce agile to their processes. So they probably move from here to there, and hopefully in the end here. So how do we get in the upper right corner? So most important, we have to do quality assurance. So it's to get some sustainability into the product. So so we want to do right things right and not just get shit done. So what is quality assurance? So from Wikipedia, the definition is, I think, is quite okay, because it's a way of preventing defects of manufactured products to get into production. So what are manufactured products? Actually, it's the process of creating a product made from raw materials. Well, this is quite a common definition. What does it mean to software development? What are raw materials? Could be frameworks, could be tools, languages, our brain, ideas, all raw materials, and we craft products from them. The craftsmanship term goes in the same direction. It's not like we automate the process of producing the software, but this is distribution stuff. So what's all automatable is distribution. Once we compile the code, everything else is automation. But what the manual work is the coding. Most of critical code is written by hand, sort of. So and every solution we produce is unique. Might look similar, but usually it's very unique. But when you have a product and we install it multiple times, it's all the same, but we don't do this. We produce the product, right? What does preventing defect mean? We cannot really prevent that defects are created. It's human to make mistakes. But what we can prevent is to get them into production. So we have to find the defects before they go into production, and for that reason we have quality assurance. So what are the sources of a product? Products are either created in internal development, where it's much easier to embed quality assurance. It's easier to have quality assurance along the pipeline. Quality is a shared effort of everyone involved in the project. Sometimes, at the moment, my current customers in insurance, they rely on external software. They buy software and run their solution. So when you have a software vendor, you have next to no influence in the quality assurance they do. You have to rely on this stuff. So it's more a waterfall style handover. Like they produce the software, we buy it, and then we put it into production. So we have very limited possibilities to check the quality of the product. Usually when when you're in real manufacturing, you buy the goods and you check the quality of the goods and then you continue processing. But how do you check the quality of the goods that you are buying when you rely on software vendors? It's pretty difficult in that area. So usually they say, or developers always claim, well, we have tested it. Yeah, it's okay. Just rely on that statement. I'd like to show you some real bugs I encountered recently. Probably you find what's wrong with this one. By the way, who's developer? Testers around? Oh, okay. Who finds the bug? It's pretty easy. Any idea? Yeah, when it's thread safe, it runs single-threaded. When it's not thread safe, you run multi-threaded. That's pretty bad. I mean, it's not that the error occurred in production. This was not the problem. It was performance impact. It was day-end processing, a batch run, and took 5 times longer. So because of there's an exclamation mark missing here. Same story with this one. Where's the bug? It's exactly the opposite. The exclamation mark is there. Problem is, it had a performance impact, 25% performance loss, which could be quite hard when running a batch, and it's a compliance violation. I mean, when you're in the social security or social insurance business, and you send some data for developers in a production system, it's probably not that compliant. So this one is my favorite. Who finds the bug? Actually, a bit background. We were asked from testing, they had the test run and said, okay, we have a performance issue, the batch takes very long. Have to look at it. So with the profiler, we found that piece of code. That's what was causing the problem. Anyone, any idea what's the problem here? Why it was not performing well? It's not that easy. So the batch was running very long. Actually, we had to stop it because it runs endlessly. So well, we see this crazy construct here. We have an endless loop. Probably how do we create an endless loop if this condition is not fulfilled? When it's not fulfilled, when from and up to are equal. When do from and up to can get equal? Here. When end is lower than from and end is lower than up to, both get the same. This algorithmic problem is not really a performance issue here. So we opened a ticket for development support, and they said, well, this will never happen in production. So it was just a test data issue. Don't need to worry here. Well, we all know eventually it will happen. And it actually did. Every second day they had to restart the application servers of the core application. Every second day a restart because of that error. But it eventually was fixed. So we have some software from any source, like internal development, external development, and at some point we have to make a decision whether we go to production or not. And when we look at the delivery pipeline, well, we have always those phases, like in Agile, you have some iterations. But at some point, you have to make a decision. It can be automated, can be a manual decision, but you have to make a decision. How do you make the decision? You base your decision on information. Well, there are several ways of getting information, like metrics. You have a number, said, okay, when we reach that number, we go to production. The complex information are test results. What did you find out during tests? It's not a number, it's information. When you have a code review, you have findings. You can make a decision based on those findings. Static code analysis is sometimes more number-oriented, but also you have to read through it, analyze it, interpret the results. So let's look at code coverage. What is code coverage? You run a test, you have a code, you put a test on it, and then you gather the information which parts of the code have been covered. problem here, we have this test oracle. This is in JUnit's assertions, for instance. But we don't know if we have the right assertions. We only know which part of the code have been covered, but not if we did the right checks. So did we really cover the semantics of our code? No. We don't know. So given that you have numbers, like you have 100% line coverage, 100% branch coverage, all tests are green, and that's the only information you have, would you release a product? You can read it. You're colorblind, right? No, it's actually really who cannot read that, what's standing here? Most of them, because this is like inverted colorblind test. It has some no here. Probably you can, once you know, you probably can see the right spots. Well, of course, it's too less information to make a good decision. So, in my opinion, line and branch coverage really provide no value that is useful for making a release decision. Second problem is, when you're not a developer and you have to make this decision, you don't know what they do, because it's like, from non-developer perspective, it's like an arcane art, like magic going on. So many things you simply have no clue. You have to rely on the statement of the developer. So our magic, our delivery pipeline is sort of that way. So some magic here, have to make a decision at some point. How do we do this? Well, I mean, this decision point is a quality gate. We define checks that we go through to make a decision. When all checks are fulfilled, we can say, okay, yeah, we can go to production. We can automate this process. It's all good. It's based on history of the project, on agreement of stakeholders and stuff like this. Most of all, it's based on information. So we need information to make a good decision. So testing is about getting new information. Who knows the difference between testing and checking, by the way? Probably you know, you're a tester, right? So what is testing? Testing is about getting more information. So we have developer perspective and tester's perspective. Developers, they write their automated tests to prove their solution is working, or they run demo sessions at end of sprint to show you, here, my solution is working. Testers have a different perspective. They try to find out how, if, and how the solution will fail. This is an information, and you can say, okay, I can accept this, or I can accept it not, put it back to development, whatever. Usually testers don't know the details of what developers do. And on the other hand, developers claim, yeah, we did it right, it's working. So now regarding the checking versus testing, we can only automate what we know. What we know and what we understand. That's the only thing what we can automate. You cannot create an automated test suite on something you do not know, or you're not aware of. So that's basic difference. This one, testing is to reveal the unknowns. Checking is to verify that the known issues or known aspects have been covered. An automated test checking is in that upper right spot. So when we have a test suite, we have sort of pyramid of different tests, automated tests. And usually the foundation, the unit test, is the broadest one, the biggest coverage. And the higher you get the pyramid, you have less tests because you concentrate on other aspects. The automation here on the unit test is usually 100%, and it gets lower the farther up you get. So when you have no real testing, just developer in your teams, it's very common in my experience that agile development teams only consist of developers and have sometimes no testers on board. So when you have no real testing, what's your information gain? It's pretty low, actually. You only have what you know, but you do not get new information. Only when you run in production, then, okay, the end user is testing it. So when we are testing, we have some manual activities, exploratory testing, to gain new information. So this is where they can help define new tests, automated tests, but as well the others non-functional requirements, usability, stability, performance, and stuff like this. So you get much more information when you apply real testing. But again, when we have automation here and manual activities here, no one is doing manual tests for unit tests. It's impossible. It does not even make sense. So you have an information gap here. When you put this all together, we can cover most of the code, if not all, during the development. And the farther we get into operations, the less we can cover code. And I intentionally put that end lower than this one. Probably not all code is used in production. Who knows? A lot of features users simply don't need. So this is also quite known, that the cost of a defect increases the farther you are along the pipeline. So now when we put this all together, where can we improve? We have the cost, we have the coverable semantics, we have the information gained by testing. So where's the gap? Here. And that's what we want to address with mutation testing. So how do we prove that we test the right thing in unit tests? And this, when mutation testing comes into play. Mutation testing is a technique where you inject faults based on rules into a product to check if the test suite is capable of finding that fault. And it's not some random activity, it's a rule-based systematic activity. The concept is quite old. Let's say in the 1970s they created it. Problem is it's very computationally expensive. So only recently, when the processing power increased, the entire topic got more attention, and especially practical tooling is now available, which I show you later. And but still, a lot of academic research is going on. Quite interesting papers, especially what they found out in testing or with mutation testing regarding testing in general. So some theory. Mutation testing is based on two hypotheses. One is the skilled programmer. So programmers only make small mistakes, no big mistakes. And usually like from some laziness or sloppiness or something, errors can happen. The other one is that the coupling effect, that simple faults or complex problems, complex defects are originated by simple faults, simple syntactic faults, like a missed exclamation mark, for instance. So the assumption is then for mutation testing, then when we mutate the code and the behavior of the test suite is not changed, so either the code is not used or the test suite is not capable of finding the fault. So some definitions. What is a mutant? A mutant is a version and a variation of the original program that is created by applying a mutation operator. Mutation operator is like a function that contains the rule how to modify the actual product. The faults are injected into the product, and usually the rule set is based on bug taxonomies, like typical known issues, or like missing exclamation marks, like an inversion and condition. When the test suite found a fault and got red, then it killed a mutant. When the test suite didn't find the fault, we have a live mutant. When we put this all together, we can calculate the mutation score. This is all the killed mutant divided by the total number of mutants. So you get a number between 0 and 1, or a percentage. And then you can say, OK, this is the quality, the adequacy of my test suite. So some more definitions that can get important. One is the equivalent mutations. Like you have a mutation that is semantically identical to the original program. That means you cannot kill this mutation or this mutant because it behaves exactly the same. For instance, when you're on the JVM, the JIT compiler, when it starts to optimize the code, And this is sort of an equivalent mutation. I mean, we don't want to look into the JIT compiler, but there are some cases where really you have an equivalent mutation, and you have to look in it and understand why it's equivalent. The other thing is duplicate mutation. This is like two variations that are equivalent to each other. Why is this important? It has an effect on the mutation score. When you have, let's say, 80%, and the rest of the 20% is probably equivalent mutations, you cannot get to 100%. It's not impossible. It's not possible. Same with duplicate mutations, so you killed more mutants than are actually there. So you have a higher score than you really have. The other definitions, like weak, strong mutations, like if you can see that it produce incorrect output. Unstable mutation is like every test can kill it, like it immediately throws an exception, for instance. Yeah, high-order mutants is a combination of mutation operators, and subsumed mutants is more relevant in the academic areas, like well, that they sum together to the same mutant. When you kill that subsuming mutant, you kill all other mutants that are subsumed by that one. It's more academic stuff. So what are typical mutation operators? Well, you have boundaries, boundary checks, conditional boundaries, negate conditionals, like the exclamation mark, for instance. Remove conditionals and replace it with constant values, like true and false. Return values, return null instead of the actual object. Argument propagation is like get the input value and immediately return it. Method calls, remove method calls. Non-voids, remove non-void method calls and replace it with a value. Remove void method calls, remove constructor calls and replace it with null. Calculations, invert negatives, invert or replace increments with decrements. Math mutations, like replacing a division with a multiplication, stuff like this. Also, you can member and constants mutation and some Java language specific stuff. Modifier, exchanging modifiers, making a field private or protected or package protected, whatever. So quite a lot of different operations you can apply to your code. So what's important to know that every mutant you cannot kill will eventually turn into a bug. They did on research, they did some experiments where they checked whether the mutants resemble real bugs, and they did. They have a very high correlation. When the test suite is capable of finding a lot of or killing a lot of mutants, it's also capable of finding a lot of real faults. When you have automated checks, it's like, I said, you only check what you already know. It's like, let's say, like hill climbing. You had a certain position and said, okay, it's safe here, I put the hook into the wall. This is here your test automation suite. But when you proceed along the hill climbing further, you have to explore in a new way. So you make a safe point with your test automation suite. So when your test automation suite is green, well, you said, okay, once in the future, when we modify the code, this test automation suite ensures we do not break anything. It's for regression testing. So when you have a live mutant there, you have a likelihood that in the future, when you modify the code, you probably break something without recognizing it, because the test suite does not cover that particular area. So there are different approaches to mutation testing. One's bytecode mutation. This is the more practical one because it's much faster. You can do it on the fly with an agent, and you don't have to recompile. From academic research and all the older tools, they use source code mutation, which is quite expensive because you have to recompile over and over again. This adds additional time to the entire process. Higher level mutations have no tool support so far, but you can still, let's say, do it as a manual exercise, like altering configuration, architecture, specification, even the use case or business case, and check whether your tests, whatever you do for testing or checking, whether they find the change in that case. Let's say for business case or use case, so you alter the use case and you have a test that verifies if the use case is fulfilled. So when you may make a different assumption, let's say you change the actor of the use case, is your test still valid or not? It's more manual exercise. So mutation testing is all tools run to those 4 phases. First one is mutation generations, like applying the mutation operators to your code base to know, okay, we have a mutant here. So you collect or create a huge number of mutants. Next is selecting the test to run. So when you have a test suite, you know for each test which part of the code it covers. So when you find a mutant at a certain position in the code, you only select those tests that actually run through this code. Next is inserting the mutants, like altering the program, and then run the test to see if at this position we find the mutant or not. So in short, first is modifying the code. In that case, we just remove this statement. Then we run the test, and then check if the test is failing. If the test is green, we have not killed the mutant. It's exactly the opposite what we usually do with automated testing. Other related techniques, fold seeding, is like randomly adding bugs and see if the developers can find them. Fuzzing, injecting faults into test data and see how the test suite or the product reacts with this. For operations, pretty similar to Chaos Monkey. Some of you probably know this one. It's like testing operational procedures. We inject a server crash into the system and see if the operations can find and fix it. Same with airport security, for instance. You have the metal detector, and it produces random false positives, just to check that the security people are doing their job good. So they have to check you and say, okay, we didn't find something, go again through, okay, it's all green now. It's basically the same pattern. There are a lot of tools around. Sorry, the color is not that good. Pit I show you right afterwards. MuJava, I think Jumble. Pit is sort of derived from Jumble. MuJava, Jester, Judy, they are all very old. They are not that actively maintained anymore. Majors used by academic research quite a lot, I've seen recently. Mutator is a commercial tool. Striker is for JavaScript, so I think it's quite new. And for the other languages, there are also a couple of tools. I'm not doing any of those languages, so I don't know much about those. So okay, let's look into Pit. Pit or PyTest. The Pit, I think, is originated from parallel isolated test. It was more a framework for running tests in parallel, but it evolved over time into a mutation testing tool. It operates on bytecode modification, which makes it quite fast. It has integration into common build tools. Around 20 mutation operands are available. It's also quite good, quite a high number. You have parallel execution, which makes it quite fast. Very active community. The tooling is also quite mature. So really good and stable. And it generates HTML and XML reports. HTML reports are usable right away, and XML reports can be processed further, like for SonarQube, for instance. So this is an example output from one of my projects. And when you see, okay, like in line 115, we found 4 mutants that are not killed. And what did it find? The first one was change conditional boundary, like the greater than is replaced with greater than and equals, not found. Negated conditional, like replaced with less than. Removed conditional and replaced with false, and same with true. And this is the information we get from mutation testing. We see exactly what we cover with our test suite. And of course, we get the number and the percentage. So how do we interpret results? What are live mutants? It actually reflects unspecified behavior. It could be code we don't need. It could be an actual bug we haven't found with our test suite so far. Or it could be an equivalent mutation. We also have kills by time out or mem error, when the modification in the code makes the code run endlessly, for instance, or longer. Then we run into a timeout. Pit does detect that, but you should look into the timeout what really caused it. When you have, for instance, a for loop and you replace the increment with a decrement, then at some point you have a buffer underflow and start all over again, so eventually reach the same position. Takes longer, so probably not killed in the end. because you eventually reached your continue the flow. Otherwise, if you have a shorter timeout settings, you probably run into a timeout and think, well, I killed the mutant, but it's probably not the case. So you really should have a look into this. Yeah, and in the end, when you have a mutation score, you have an indication of the overall quality of a test suite. I mean, based on this information we have now, we can sort of assess our test suite. I thought, well, something like a unit test maturity model would be good. So, well, when we have no tests, we have no unit tests, we have no mature testing at all. If we have at least one test, that's something. If we even cover lines, that's good. If we have more than 50% branch coverage, we might accidentally find some issues, probably when we trigger an exception. When we have at least one effective assertion per test, it's not that typical. I mean, I've seen code like assert not null and then new object. So, well, we have an assertion that's just totally useless. And the highest level is, in my opinion, is when you have a really high mutation coverage. So, time for demo. So, okay. What we have here, it's a short demo application. And what I do with Maven, I just add the PyTest plugin. Let me check in that case. This is like we specify which. That's very, very small. We have a better one with. Oh. Yeah, here we have. So, what I defined here is the plugin. I define the property in that case that I want to target a specific package. In that case, it's io-defcon5.star. And I also define which mutators I'd like to apply. I use the defaults and yes, time mode values. This is probably all you need. Yeah. What in that case, what I typically do is I bind the mutation testing to the verify phase, so it runs after I run the unit test. As a precondition for PyTest, you need a green test suite. You cannot run mutation testing when you have no green test suite. That's really precondition. So when we let this run, so now it executes test. There we go, and this is the result. So what I have, the code is a function to find out the maximum value of a set of values. Looks pretty okay so far. I mean, if you look at the test, so okay, the test doesn't look that bad. But why did we not kill every mutant? Well, the problem is, how would you read this test? It's like, given we have a pre-sorted array of numbers, then we find the highest number of that pre-sorted array. That's what this test actually says. We have the sort is especially important because when we replace this with that, the test is still green. There. It's compiling. Green test. So we need another test with the numbers in the opposite direction, or opposite ordering. Another thing, I try to apply mutation testing to one of common Apache projects. I can run this for common CLI, this command line interface library. check. I have Pit available. This runs around a minute. It's still fast enough for demo case. The other two, I/O and lang, run far longer. So like the I/O runs around 30 minutes and the Commons lang around an hour. And the Commons lang has, I think, 25,000 lines of code, and the Commons I/O has around 10,000 lines of code. There you see the biggest problem with mutation testing is the computational cost. The larger your code base get, the longer the mutation testing takes. And once this runs, and this increases the more mutation operators I apply. But, so you always have to find a good strategy how to use mutation testing in your project, how to limit the scope of it, select a certain package, for instance, only use a subset of all the mutation operators, not all of them, and probably. Well, when you have a small project, a very small project, you probably include it in the continuous integration pipeline. If you have a larger project, you probably should not do it because you do not get fast feedback from it. It's something you should really take care of. Oh, it runs actually longer than expected. But well, yeah, we can continue the demo afterwards. So, I talked about the timeouts. What are limitations? Also, research found in the study around whether mutation testing resembles real faults that around 1/4 of all faults are not coverable by mutation testing. This is a fundamental limitation because you cannot, for instance, check whether you chose the right algorithm. If you pick a wrong algorithm, well, you cannot check this with mutation testing. You have to use other testing techniques to find out those things. Also, from mutation score perspective, PIT does not recognize subsumed or equivalent mutations or duplicate mutations. So from an academic perspective, the score might not be that precise, but probably doesn't matter for your project. It's a number you can work with. It's an information you could use to make decisions. And also some has already quite a lot of mutation operands, but research also going on finding new mutation operators that are not yet supported in PIT, like concurrency, for instance, like moving or resizing a synchronized block and stuff like this. Another thing is academic technique to reduce the computational cost to get the mutation score, not the single information, but the score, is to use sampling. So you generate a lot of mutants and only say, let's run the mutation test for only 10% of those to get really fast feedback of the mutation score. They showed this is still, the mutation score is still quite okay, but PIT doesn't support it. You can only run the full mutation suite. And as I said, the value you get from mutation testing has its cost, and it's exponentially increasing computational cost. So, like when your code base increases, the computational effort increases non-linear. And when you add additional operands, it looks even worse. But still, if most mutations can only be found when you apply a lot of mutation operands. So from the information you can get is you can have the mutation score, said, okay, how good is my test suite with a single, represented in a single number. And the other thing is for developers important, what particular fault or what particular location of the code is not covered by the test. So yeah, for legacy code, it's like you have really steep curves. You split it into chunks and run it on every other day, so you can have a good overview. And what's also good for large legacy code base is you are forced to componentize, to break down the code base, make it more manageable, also for mutation testing. Yeah, challenging challenges of mutation testing, still topics of academic research, subsuming, duplicates, equivalent detection, because of their effects on the mutation score. The computational cost is still a problem. They have to find out, okay, how to reduce, how to apply better strategies for reducing the computational cost. Yeah, okay, let's come to the conclusion. Don't trust the unit test suite unless you have run mutation testing on it. Use mutation testing in your project, in every project. You don't have to run it every time you make a commit, but from time to time you should get this information. It's really important. Also, don't aim to achieve 100% mutation coverage. Don't go on the killing spree and kill every mutant. It's really expensive to do. Triage the surviving mutants. What mutant you really want to kill, what is important. You have to look at the results, make a decision, which one do you want to kill, which one not. Also, integrate it in the continuous build, but probably not in every build. Probably make a scheduled build in the night when you have other resources. When you run on Amazon, for instance, you can run it on a not snapshot, what's it called, and spot price instance, for instance, because it's cheaper and you get probably more power to run it. Yeah. So use cases, I talked about finding gaps in the test suite, testing highly exposed code like algorithm, calculation, security-related code, transaction-related code. Well, the assessing the test suite part is more from academic perspective. But what is interesting here is they also run a study if test first lead to better test suites. It doesn't. Same as pair programming. It does not lead to better test suite. I also read about another study. It does even not lead to better code. But it has other positive effects because you think before you code. You make up your mind what you actually want to test. But yeah, and they used mutation testing to find that out. To check, okay, what test suite they created and are they better with test first or not with test first. Also, you can minimize your test suite, so you can get rid of tests that don't add value. Problem is you also reduce the effectiveness of the suite for detecting real faults. They also proved this or showed this in studies. So, okay, yeah, key takeaways. Mutation testing is practice to find bugs in your test suite. Use it always in the projects. Don't kill every mutant. And for Java, use PIT. Okay. Thank you. Any questions?
So are the mutators applied randomly? Is there some randomization?
No.
No, they're always applied.
Yeah, it's like you select which mutant mutation operators, and you select the part of the code, and it's always the same.
Okay. It's always, okay.
Yeah. So it's very systematical. It's not, and yeah, you can reproduce the results.
Do you have a priority list for which mutations are most important to kill first, or it doesn't matter?
Well, I don't have a priority list. What I do with PIT, for instance, I use the defaults very often. I sometimes add another one, but there's no common rule or no golden rule which one to apply. It really depends on the project. Other questions? No? Then thank you for your attention.